Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh and a very good morning. Alright, my time is 8:56 a.m. Alright, today we learn into another topic, which is the analysis of organic analytes using chromatographic based method sample preparation. Okay, chapter kali ni kita belajar untuk, sebenarnya bukanlah untuk analisis. Saya pun tak faham kenapa tajuk dia macam it's not really kena dengan content dalam benda ni, but I think the correct title is about sample preparation for the analysis of organic analytes using chromatographic method. Kalau kata you nak faham lah. Okay, tapi kalau kata macam ni macam pelik kan, but it's about sample preparation for the analysis of organic analytes. Okay, when we talk about organic analytes, the sample preparation is different if we compare to the inorganic analyte. Okay, you jangan keliru. You guys, please don't be confused, because in the earlier topics we already learn about the sample preparation, the first topic of the sample preparation, but that topic only for the inorganic analytes, which is the elements, the ions. Okay, but this sample preparation for this topic is only focused on the organic analytes. Okay, so among of the sample preparation technique is the solid extraction, liquid extraction and solid phase extraction. Okay, kita ada juga sebenarnya kalau kata gas extraction ataupun kita ada SPME, but kita akan fokus pada tiga ni lah. Okay, kita akan fokus kepada tiga ini sahaja. Solid extraction focus on the solid or liquid sample. Okay, do both, and we can do liquid extraction. We can also have the solid phase extraction. Kita juga ada solid liquid extraction. Solid liquid extraction actually fall under liquid extraction lah, but the sample is solid. Okay, liquid extraction, the sample is liquid. Alright, okay, let's go to the next slide. Application of extraction method. Okay, actually I think it's the purpose of the extraction method. Actually, the purpose of extraction method is for the micro and semi-micro analysis. The purpose of the extraction method is for the removal of the impurity from the sample, and the application of the extraction methods for maybe we want to increase the concentration of the analytes. So you can write as the application, you can write as the objective, but for me, if I'm reading this right, the content over here is more likely to be the objective of the extraction method. Okay, untuk yang the first part, micro and semi-micro analysis, you nak buat analysis lah, and the removal of impurities. Of course, you want to only extract your compound, you want to remove the impurities. Because why you want to remove the impurities? Impurities can somehow disturb your reading or your analysis. Okay, the last one, you want to concentrate your analytes. Okay, mungkin you ada sample dengan adanya you punya solvent of extraction, you want to pre-concentrate you punya analyte. Daripada 1 liter you punya sample, you want to collect your analyte, dan you want to concentrate mungkin dalam 100 ml sahaja you punya solvent extraction. Okay, yang ni kita kata pasal ni lah. Okay, the next one is the classification of solvent extraction. Okay, solvent extraction, we can go to the solid sample and liquid sample, depends on the type of your sample. Okay, but solvent extraction can actually done for gas sample, but we will only focus on the solid or the liquid sample. Gas sample is far more advanced. Even myself have learned about it, but doesn't yet have any opportunity to apply in my research yet. Alright, in the solid sample, we have the solid liquid extraction batch, and we have solid, liquid, extraction, continuous. Kalau you perasan kat sini, we have the batch and continuous. What is mean by batch? Batch maksudnya you masuk you punya solvent, you extract, lepas tu you terus analyze. Okay. But in the continuous, it mean that you extract, you dapat you ada sample, you letak solvent you akan dapat extract. Okay, extract tu you akan rotate balik masuk dalam you punya sample, dan dia akan berulang-ulang sehingga sampai satu masa nanti dia kata you want to make it continuous until 10 minutes. So itu dimasukkan dengan continuous. Kalau kata batch, you masuk solver sekali saja, lepas tu you extract, itu sekali saja. Tapi kalau kata continuous, you masuk, you extract, lepas tu you guna the extract, you masuk lagi, you extract lagi sampai beberapa kali, ataupun sampai you reach the desire punya you punya parameter. Contohnya you kata you nak test punya masa, ataupun you kata you nak extract sampai the temperature reach until 70 degrees Celsius. It depend on the parameter. Ataupun you kata you nak try extract continuous 10 kali pusing. So that is meant by continuous. Okay. Right. On the solid liquid extraction, you can apply the actually nanti kita akan discuss into detail lah. Okay, but in the liquid sample, we can perform liquid extraction. Okay, liquid extraction, we have the cross current, we have the counter current. I'm not really sure if we really focus on the liquid extraction or we will focus on the cross current, on the counter current, because the next slide yang saya akan tunjukkan you guys adalah slide yang saya tambah sendiri lah. Dia tak ada dalam slide in the previous by the other lectures. So the I think the most important part of the liquid extraction or the solid liquid extraction is the batch or continuous only. Okay. For the current thing, let's focus on the liquid sample, on the liquid extraction. Okay, or we call as the LLE. Bila saya sebut LLE, is mean that liquid extraction. Alright, the next slide we will learn about the cross current extraction. Here is the cross current extraction schematic. Okay. Before we are going further, let me explain about the basic of liquid extraction. Okay. Let's go into a little bit on the basic liquid extraction. Okay. You have the container over here. Let's say you don't have any fill, and then you have here is your sample. Okay, then you put your sample over here. Okay, so this is the process. Here is the container. You put your sample inside the container, and then the next process of LLE, actually you put your solvent of extraction. Let's say your solvent of extraction, you add solvent of extraction. Okay, right, this is just the basic information only. Alright, so you have your solvent over here, you have your sample over here, you have your solvent of extraction over here. So let's imagine. Okay, let's make it bigger. Okay, before we put our solvent inside the container, solvent of extraction, maybe we have the sample inside here. We have sample. We have the analyte of interest. The analyte of interest inside your sample. Let's imagine the blue is your sample, and the orange dot is your analyte of interest, compound of interest. Okay. After we put solvent of extraction, we hope that ideally all of better I change this color into maybe green one. Okay, we hope that all of our analyte of interest will transfer into the solvent of extraction. Okay, but in the reality we might only get about 80% to 90%. If you can get 100%, it's good, but usually you get 80% is good enough already. If you get less than that, it's not really good extraction method. Okay, why we doing the liquid extraction technique? Because we want to extract our analyte only without extract the impurities. Let's imagine the purple one is our impurities. So we want to extract our analyte of interest only without extract the impurities, because we know that impurities will disturb the reading and also we somehow contaminated our instrumentation. So we want to extract our sample only. Okay, and this is the basic idea of the liquid extraction. You might get 80% to 120%, so that your punya extraction is very good. As long you get 80 to 120%, the extraction is good already. But if you get less than that, it means that your extraction is not that good. Okay, let's say like this lah. Okay, this is the basic idea of the liquid extraction. Okay, so you have the basic already. So let's go back to the to our slide, is the cross current extraction for liquid extraction. Okay, I don't want okay, again I want to mention that in the originally the slide of the cross current is not in the slide of the other lecturers. I put here because I don't want to leave the information hanging, so you guys cannot understand what is the cross current. Okay, so if for example the this cross current appears in your final examination, so you can answer, right? Okay, in the cross current, okay, here is the counter current, here is the cross current. We focus on the cross current first. In the cross current, here is your sample. Okay, you put inside the container over here, you put the fresh solvent. Let's say for example you have 1 liter of fresh solvent, and then you get the extract. Okay, you get the extract. Okay, then after the first stage is done, then you proceed the remaining sample over here, you proceed to another stage. Okay, in the next stage you put another fresh solvent and then you extract, so you get another liter of fresh solvent, and then you repeat again to this stage 3. Okay, and then what happen is the number of extraction solvent will be increasing because you always add the fresh solvent. Okay, so dia akan bertambah sebab you asyik tambah cecair baru je lah. Solvent maksudnya cecair baru, larutan baru. Okay, sampailah you punya sample you depleted of the concentration of analyte of interest. Okay, maksudnya mungkin kat sini the first stage you can only extract 50%. So the concentration, let's say concentration is 10 ppm, you extract 50%, it become 5 ppm. You extract again 50%, so here it become 2.5. Okay, so you extract lah. Okay, we also learn about batch and continuous, right? Okay, if happen in batch, mungkin you sampai sini saja. Maksudnya bila you perform the batch cross current, what you done only until third stage only. But if you doing the cross current, if you are doing the continuous cross current liquid extraction, you will continue this process until all your analyte of interest inside your sample extracted completely lah. Okay, that is what mean by the continuous extraction. Or we can also say like this. Okay, you have the cross current, you put the fresh solvent over here, and then you extract it. Next one we will learn about the counter current liquid extraction. It's actually more complicated compared to the cross current. Okay, because the design of the real instrument for the counter current is somehow a little bit more complicated. Okay, let's discuss about the best counter current LLE first. Let's say you have your feet over here, stage 1, stage 2, stage 3 in one batch. So it's actually you just divide into 3 stages, and then you put your fresh solvent over here. Okay, compared to the previous in the cross current, you add fresh solvent at every stage, but in the counter current you only put fresh solvent once. So what happened here actually in the batch LLE for the counter current is you put your fresh solvent over here, you extract, and then you put the extract over stage 2 and extract in stage 2 and transfer into the stage 1, and it will extract again. So the total number of fresh solvent will be remain the same. There is no addition of the fresh solvent. This is what we call as the batch counter current. But for the counter current to be efficient, you need to do it continuous. It means that your sample will somehow cycle through this stage 1 to stage 3. So your sample continuous from stage 1 go to stage 3 and then cycle to stage 1 again. Maksudnya yang ni akan pergi stage 1, stage 1 akan pergi stage 2, stage 2 akan pergi stage 3. And then you punya solvent ni dia akan berpusing-pusing. Dia akan extract again and again. Sampai you can after certain period of time, then you stop. That is what is meant by continuous. Again, for the counter current LLE to be productive, it must be continuous. Okay, sebab kalau tak, dia macam tak efficient sangat lah. So what happen again, yang ni dia akan berjalan continuously. Stage 1 pergi ke stage 2, dia akan pergi stage 3, stage 3 dia akan pergi balik stage 1, stage 1 pergi stage 2, stage 2 pergi pada stage 3. Dan fresh solvent dia akan continuous extract. Dia pergi extract kat sini, lepas tu pergi extract kat sini, pergi extract kat sini, dia akan continuous. Okay, kalau kita kata batch, you boleh imagine is as we divide into 3 stages. Okay, that's why I said for the batch counter current LLE is not that productive if we compare to the continuous counter current. Okay, alright, in the next one we will learn about the equilibrium. Okay, have you guys performed the titration where some from the milky solution it turns to dark blue? You can imagine like that. Okay, a dynamic equilibrium occurs when two reversible processes occur at the same rate. It means that two reversible processes occur at the same rate. Maksudnya S1 can go to S2, S2 can become to S1. Okay, many processes such as chemical reaction are reversible when at dynamic equilibrium, which is the forward reaction will occur at the same rate as the reverse reaction. So dia macam cycle lah, S1 go to S2, S2 go to S1 at the same rate. Dia akan bergerak dalam keadaan yang sama. In many processes, the system seldom reach equilibrium. So dia sama ada ke depan atau terlebih sikit ke belakang. Just imagine as the titration when you change the milky solution into the dark blue one. So if it's really become a dynamic equilibrium, so dia akan jadi macam sekejap biru, sekejap putih, sekejap biru, sekejap putih lah. Okay, but the system seldom reach equilibrium. Contoh, you tambah acid sikit, dia jadi biru. You tambah basic sikit, dia jadi putih. Okay, so seldom reach equilibrium. KD is the distribution coefficient, concentration of the organic solvent to the aqueous solution, ataupun terbalik lah. Okay, terbalik pun boleh. Okay, so but I don't think we actually learn how to calculate the KD. Maybe you just need to remember what is the equation only, but we don't actually apply the calculation. Okay, so again, distribution coefficient equal to concentration of the organic solvent to the concentration of solvent inside the aqueous. Okay, right. Okay, so what is meant by equilibrium in the liquid extraction? Okay, You can imagine like this. You have your sample over here inside the aqueous phase lah. So imagine this is aqueous phase. Can I make it bigger? Okay. You have one, two, three. Sorry. Can I have the eraser? Where's my eraser? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. We need another one. Okay. In the equilibrium, in the liquid exertion, it means that you somehow get the condition where you can somehow transfer all your analyte of interest into your punya desire phase. Contohnya you nak transfer daripada sini ke sini lah. Contohnya nak transfer, you dapat transfer ke semua 10 you punya analyte. You can transfer all your analyte of interest from the aqueous phase to the organic phase. That is mean that you achieve the equilibrium. But if you don't achieve the equilibrium, it means that maybe you left 2, 3 or 4 in your aqueous phase. So it means that not all of your analyte are transferred into the organic phase. Okay, mungkin you tertinggal 40% of your analyte dalam aqueous phase. Maksudnya you tak achieve the equilibrium. Okay, kalau you achieve the equilibrium, it means that you can somehow successfully obtain 100% to the next phase. Okay, so contohnya lah, kalau kata you terkurang sikit je organic phase, you punya distribution, you tak achieve the dynamic equilibrium, then you punya analyte tertinggal kat sini. Yang ni yang dimasukkan lah. Tapi kalau kata you get the correct concentration of the organic phase, you can transfer all your analyte of interest inside here lah. Okay, ni bila you kata this is what we call, we can relate the equilibrium with the liquid extraction. Alright. Okay, we already learned the basics, so let's go into the liquid extraction. Liquid extraction, also known as the solvent extraction and also partitioning. Why we use why its name is the solvent extraction? Because we use solvent to extract our analyte of interest. Why it called as the partitioning? Because we partition the liquid into more than one layer. Maybe 2 layer lah. Usually become 2 layer. Okay. Dengan kata yang mudah, why partitioning? Here is your sample and then here is your solvent extraction. So apa yang kita katakan partition, we create the partition between two. We have the we create the invisible partition. We create the invisible partition between two, sample and also our extraction solvent. Sample dengan solvent untuk extract our analyte of interest. That is why we call as the partition punya extraction technique. Okay, a method to separate compounds based on their solution preferences for two different immiscible liquid, usually water and organic solvent. Okay, katakanlah okay, we have okay, usually lah, this is from my experience, for liquid extraction to successfully occur, you need to somehow create the two different immiscible liquids. Okay, create two different immiscible liquid. Ini maksudnya liquid yang tak bercampur. Immiscible is mean that dia tak bercampur, dia tak asing. Okay, bila kita dah separate, dia akan compound of analyte of interest, dia akan tengok dia akan pergi mana. Dia akan separate based on their solution preferences. For example, we have water over here. The blue one is water. The above one is hexane. Kalau kita compare water dengan hexane, the density, ketumpatan, the density of water is more higher compared to hexane. So, hexane dia akan berada di atas. We know that hexane is non-polar solvent. Meanwhile, water is a polar solvent. So if your in this example, your orange one is your sample, the purple one is the impurities. Okay, and in this condition, we can say that our sample or analyte of interest is non-polar. Atau dalam kata yang lain, contohnya, or we can put it like this. Okay, okay, let's say here is your sample inside a water, and your analyte is non-polar analyte. So you want to extract your analytes so that you can somehow remove the impurities. How to do that? So we extract by putting an organic solvent that is non-polar solvent. So your non-polar analyte will somehow move towards non-polar solvent extraction. So dia akan transfer dalam sini. So persoalan dia kat sini. So the question is, can we use, let's say for example we have water, can we use the methanol as extraction solvent? Okay, it cannot. Why? The first reason, the methanol is a polar solvent. Polar solvent will somehow dissolve in polar solvent. It means that your methanol will somehow totally dissolve in water. Okay, and then the second thing, your analyte here is non-polar. It will not be dissolved in the methanol. Okay, sorry, not be efficient to be extracted using methanol. Okay, it will goes to the non-polar solvent, for example hexane, methane, pentane. Okay, let's say your analyte here is polar. How do you want to extract your solvent? How do you be able to extract your analyte of interest by removing the impurities? Okay, as we can see over here, can I duplicate first? Okay, let's say your analyte is polar. It's inside your sample, inside your water, but you want to remove the impurities. So what you can do is you put your non-polar solvent. So you somehow, and the impurities, the non-polar impurities will go to the non-polar solvent. So you can use the water inside here for the analysis. So the intention of the liquid extraction is to somehow to extract the impurities and ready your sample for the analysis. Okay, again, the liquid must have different properties by its density and also its polarity. Okay, if you ask my opinion, I will always choose my analyte of interest, my solvent of extract that have less density compared to the sample punya solution. I will always choose of my solvent extraction that has less density compared to my sample solution. For example, density of hexane is less compared to the water, so the hexane solution will always be on top so you can extract much more easily compare you want to extract at the bottom of the container. Lagi senang you nak extract solvent dekat atas berbanding dekat bawah. Okay, let's say okay, alright, okay, I give you another example so you guys can understand. Okay, let's say you have your container over here. You have no fill. Okay, come on, happen. Okay, let's say in the other container you have your sample, which is where is it? I'm sorry, can I remove this first? Okay, let's say you have a polar solvent. Let's say you have you have a polar analyte of interest. Okay, and your sample is inside the water. So how you can improve? Because we know that if we use water, the density of water is very huge, right? So what kind of solvent you can somehow make it the solvent extractant of water will be at the top layer, let's say. Okay, so what can you do? You need to somehow use the non-polar solvent that has a higher density compared to water. The example of non-polar solvent that is more density compared to water. What is it? What happened? Okay, it's okay. Let's say so how to make your polar solvent at the above. So you need to use the solvent, non-polar solvent that has a higher density compared to water. So the example of the non-polar solvent that has a higher density compared to water is carbon tetrachloride, CCl4, and or carbon disulfide. Carbon tetrachloride and carbon disulfide has a higher density compared to the water. So if the solution has a high density compared to water, they will reside at the bottom of the container. So you punya solvent and analyte will be somehow go over here. Dia akan pergi ke atas. That is how we can adjust. So you play around with the polarity and you play around with the density. But to make them immiscible, you need to use the one that is opposite polarity compared to your sample. Okay. Right. That is what we mean by a method to spread compound based on their solution preferences for two different immiscible liquid. Kalau you punya analyte is non-polar, you kena guna solvent extraction yang non-polar. Kalau analyte you is polar, you kena guna solvent extraction yang polar. Okay. It is an extraction of a substance from one liquid phase into another liquid phase. Yang ni yang dimasukkan is extraction of the substance from another phase into another phase. Okay, into another liquid phase. Alright. Let's go for the pictures of liquid extraction and the procedure. Here is the separating funnel for the liquid extraction. Okay. Here we have the higher density liquid, we have the lower density liquid, and let's say here is the non-polar solvent, non-polar, here is polar. Here is polar, here is polar, here is non-polar. Let's say your sample is non-polar, it will go to the non-polar solvent, non-polar extraction. So kalau kata you punya analyte kat atas, you keluarkan semua, you buang dekat bekas lain, then you take the sample. Yang ni funnel tap to control you punya pengeluaran solvent lah. Again, here is the separating funnel. In the separating funnel, we have our sample. We have the liquid, two liquid, either is polar or is non-polar. The higher density liquid will reside at the bottom of the separating funnel. Okay. The lower density liquid will be always at the top layer of the total solvent. Again, if your sample is non-polar, let's say for example the solvent above here is non-polar and the solvent below here is polar. Let's say your analyte is non-polar, it will go to the non-polar one, non-polar solvent. If your analyte of interest is polar, it will go to the bottom. Okay. So let's say for example your analyte of interest reside at the bottom, which is a polar. Your analyte of interest is polar, reside at the bottom, which is the polar solvent. So you can somehow open the funnel tab, so you can somehow extract into the aluminum flux, and then you can stop until it reach the bottom, until everything somehow you can extract over here. Let's say your analyte of interest at the top layer, so you can somehow remove the first layer first, and then you can proceed with the top layer. You can take the top layer. You can use this link to watch the procedure of the liquid extraction using the separating funnel. Okay, but this is the old method of the liquid extraction, but again it's widely being used in all over the world. Okay, but nowadays major research and scientists already explore on the capability of the micro liquid extraction. Maksudnya diorang guna extraction liquid extraction, instead of they use 100 of mil, they will only use about less than 1 mil of extraction process. So let's look at the procedure over here. Okay, the sample was inserted into the separator funnel. We add dichloromethane, shake for 2 minutes and release the pressure. Okay. Then you can bila you dah campur, you shake, release the pressure, you let it settle for a while, akan wujud two kind of layer, organic layer and aqueous solution. Aqueous solution we refer to sample we refer to water solution. Okay, organic solution we refer to non-polar solvent of organic solution. Okay, then the aqueous solution, contohnya lah kalau kata kat sini aqueous solution, kita ambil, kita masuk balik dekat atas, sebab mungkin kita punya sample dekat dalam aqueous solution ni ada baki. So our sample solution in the organic solution, kita ambil, kita letak dalam bekas yang lain. The aqueous solution, we repeat the process maybe 2 or 3 times, depends on the optimum process of extraction. Mungkin dia kata lepas 3 kali extract baru you dapat 80% of extraction, so you kena repeat. Maksudnya you letak 50 ml is your sample in the aqueous solution, so you proceed the extraction with 10 ml. You shake for 2 minutes, release the pressure whatever, you 10 ml ni you letak dalam satu bekas yang lain. The remaining aqueous solution will somehow insert back into the funnel. You add more again dichloromethane and then you repeat this process for another 2 times. You have 30 ml of extraction dichloromethane. This dichloromethane you pre-concentrate by evaporation. Okay, contohnya you pre-concentrate daripada from 30 ml, contohnya you repeat 3 kali, 3 to 5 times, you evaporate until 5 ml, and then you proceed to the analysis. Okay, you can click, you can somehow using this link go to the YouTube channel from somebody else to learn how actually liquid extraction is done. Okay, but here is the normal procedure lah. Okay, again I need to mention it's really important for releasing the pressure. Okay, so how to release the pressure? Okay, you can look into the channel YouTube over here. So basically what you do after you insert all the desired liquid and the extraction solvent inside here, you will shake a little bit, and then you will somehow terbalikkan dia. You will reverse the bottom to the above, so you can open the funnel tap and release the gas, and then you close the funnel tap, then you extract your desired solution. Okay, right. Okay, the advantage of the liquid extraction is simple, robust, minimal operator training, efficient, and a wealth available analytical data, widely accepted in many standard method. Okay, so far almost all standard method for the liquid extraction will use the conventional technique lah, using the separating funnel. Okay, very simple, tak susah pun, robust, dia tak ada masalah sangat, minimal operator training, it's not really complicated, so tak perlu training yang payah, very efficient. Maksudnya minimum operator training ni you tak perlu pun orang train. Contoh you dapat the next method, you tak perlu pun orang lain train, you just baca the method, you can operate by yourself. It's really efficient. Depends actually if the method is already optimized, become a standard method, so it can be efficient. Alright. The disadvantage requires large volume of high purity solvent. Ini masalahnya sebab kita guna a huge amount of solvent and we deal with the hazardous solvent. So that's why many researchers and scientists nowadays already proceed to the small volume of liquid extraction that they call ST, micro liquid extraction. You can find a lot of paper that have performed on the micro liquid extraction. Okay, yield small sample to solvent volume ratio, often forms emulsion, time consuming. Okay, what is mean yield small sample to solvent volume ratio? Okay, because you punya solvent banyak tapi sample you sikit je, ataupun extraction you sikit sahaja. Okay, often forms emulsion. Emulsion ni contoh yang akan bila you je kadang-kadang the problem is the liquid extraction. The problem with the liquid extraction that sometimes it can forms emulsion. Emulsion is mean that we have the between the two layer, you have another layer at the middle that somehow in the form of emulsion, dia macam berminyak sikit kat tengah-tengah. That's the problem. Okay, so you need to somehow put the another kind of solvent to remove the emulsion. Okay, the next one is time consuming lah, because you need somehow, maybe somehow it will take sometimes to release the pressure gas. It will take sometimes to before the two layer can be totally immiscible. Okay, sebab kadang-kala, because sometimes it will take sometimes, because you already mix everything, you goncang, you shake everything, it will take sometimes before the two layer can become totally immiscible. It will take sometimes. Right. Major idea: facilitate automation and effectively to reduce the consumption of organic solvent. Okay, that's why instead of batch extraction, it's preferable to do continuous extraction. So the question here, in the liquid extraction, is it one big batch of solvent versus multiple small batch of solvent? Here we use the example, you use 1 liter of water containing 1 gram of solvent. So what you're really doing here, you put the organic layer, another 1 liter, and you have the aqueous layer, which your water is 1 liter. The efficiency of the extraction is only 50%. So it's 10 gram of analyte of interest, you can only get about 5 gram can be only extracted. Okay, so the recovery is only 50%. So if we look into 50% recovered, 50% left in the raffinate. Okay, let's say we put into different batch, or we have multiple batch. The 1 liter we divided into 2 different portions. Okay, we have we put okay, multiple batch. Okay, so what you are doing here, actually you put 1 liter of your solvent containing 10 gram of solute over here, and then you extract. Okay, let's look if we break 1 liter of organic solvent into 2 equal portion of solvent extraction. Here we divide into 500 ml and also 500 ml. Okay, here again we use the same amount of sample, 1 liter, but we reduce our organic solvent into half, because the amount of the solvent extracted compared to the sample is only 1 to 2. We expect maybe only about 30% of efficiency. So if we look here, in the first extraction, we can extract 3.333 gram of solute. So we left 6.666 in our raffinate. We use the raffinate and we proceed with another 500 ml of organic solvent. Here we can only extract 2.222 from 6.66. So the remaining here is 4.44. After we break into 2 equal portions, we can obtain about 5.555 gram, which is 55.55%, which is better than previous one, which we only obtain about 50%. Right. Okay, let's see if we break our organic solvent. We break up our organic solvent into 4 equal portions. Instead of previously we break up into 500 and 500 ml, but now we break up into 4 times of 250 ml. So the first extraction we can only be able to extract 2 gram. The second we can extract 1.6 gram. Until the fourth we can extract 1.024. If we add up the total extracted, it's become 5.904 gram. So the recovery is 59.04%. So the multiple extraction using the same volume of extractant produce better extraction recovery. So you can imagine if we do this continuously, so we can get a better extraction recovery. Okay, here we learn about the LLE solvent selection. We choose the LLE solvent selection based on the characteristic of solvent commonly used in LLE. Okay, so the main characteristic we use in the LLE is based on the polarity. Okay, if we, let's say our sample is in water, so can we use the hexane as the solvent of extraction? Yes, because why? because hexane is not miscible in water. Dia tak bercampur. So you akan dapat dua layer yang tak bercampur. So you can extract. Kalau kata layer tu bercampur, macam mana you nak extract? So if let's say again your sample is in water, you can use isooctane, you can use CCl4, you can use chloroform, you can use methylene chloride, you can use ethyl ether. Okay, let's say your sample is non-polar. For example, your sample is in diesel or petrol. Your sample is non-polar. Okay, so you want to extract a polar compound inside of the petrol. So you need to use the solvent that is not miscible to the non-polar analyte. So you need to use the polar solvent. So you can use water, you can use methanol, you can use isopropanol, you can use acetonitrile, or you can use acetone. But again, the thing that you need, the solvent, the another factor to choose your solvent, it depends on the capability of your instrument. For example, we have already learned in the HPLC, if you use the reverse phase HPLC, you will use non-polar column. If you use the non-polar column, you cannot use the non-polar solvent. So you cannot use the hexane as the solvent extraction. So you need to use the polar solvent as the solvent extraction. Let's say you use gas chromatography. In the gas chromatography, it's not advisable. It is not advisable to use water to inject into your system, because water has a very high polarity and very high back pressure. So dia akan rosakkan kolom. So you cannot use water as the solvent of extraction if you use gas chromatography. So that is another factor for before we can decide which kind of solvent that we can use for the liquid selection. But the most important thing, it depends on the polarity of analyte of interest. If your analyte of interest is non-polar, you use the non-polar solvent. If your analyte is polar, you use the polar solvent. Here is the LLE of metal ions using the chelating agents. Yani, this is the slide that we go a little bit into inorganic analyte. So example, you want to extract this kind of metal, you need to use the extractant, and then you need to use this reagent. Without this reagent, you cannot extract the metal ion, because it cannot somehow form the chelating agent. Okay, that's why you need to use the chelating reagent over here. But please don't remember any of this, because I don't think it's actually quite okay for you guys to remember any of this. It's too much actually. Okay, this is just the example. So for me, it's not really fair for you guys to remember a lot of this. Okay, but what I need you guys to know, that if you want to perform the LLE of the metal ions, we need to use chelating agents. What is chelating agents? Chelating agent is the agent that can somehow bond with the extracted with the metal ions. Okay, that is why we need the chelating agent. Without the chelating agent, we cannot chelate the extracted metal. We cannot chelate the ion, so we cannot extract the ion. Here is another example. Effect of pH on LLE using chelating agent. We can see over here, right? As the pH increase, different ions, different element, they have different optimum pH. Okay, for example, for the copper 2 ion, the optimum pH is about 4. If we look at the plumbum, the optimum pH is about at 8. Okay, here so the pH of different ion, they have a different pH. Okay. In this example, they use diazone as the chelating agent. Alright, we actually have done on the liquid sample. We will focus now on the solid sample. In the solid sample, we can call as the solid liquid extraction. We can do batch and we can do continuous. In the solid sample, we have a very special name, very special instrument for the solvent to perform the solid liquid extraction. We will look into that after this. Okay, the name of extraction instrument or extraction method we call as the Sochlet extraction. Sochlet extractor is lab equipment designed for processing certain kind of solid. This is why I say that very special instrument, or we can call very special equipment designed exactly for processing certain kind of solids. This device allows for continuous treatment of sample with a solvent over a period of hours or days to extract compound of interest. For extraction by using solid sample, it is much more efficient if we use the continuous treatment or continuous extraction, as we already discussed before this. Okay, because in the solid sample, the difficulty to extract is much more higher, so we need a better and efficient method of extraction. So continuous treatment is one of the best method of extraction we can do to extract from solid sample. Again, we can see over here, the solvent, the extraction can take hours or days, depends on the standard method or method validation have done before this. Typically, a Sochlet extraction is only required when desired compound has a limited solubility in a solvent and the impurity is insoluble in that solvent. Okay. Again, we use the extraction solvent when we have the limited solubility of our analyte of interest in the solvent. If let's say the efficiency of the solubility of your analyte of interest from solid to liquid can be done 100% immediately, so you don't need the solid extraction, you can just perform the solid liquid extraction just like LLE. But for the solid extraction, the purpose is when the solubility of analyte is limited because of the solid impurities that is insoluble in the solvent. Okay, bayangkan you ada solid sample. You imagine yourself you have the solid sample, and then you punya analyte of interest, dia bukan sahaja berada di surface, it's not just appear on the surface, but also can be somehow trapped inside of the solid. So it will somehow limit the solubility of your analyte of interest into a solvent. Okay, that's why you need the Sochlet extraction. Okay, now we will look about into the components of Sochlet extraction. Okay, it's actually a little bit complicated. Alright, the first component is stirrer bar, is to stir the solvent of extract. Number 2 is the what we call as the still pot, round bottom flux. And then we have number 3 as distillation path, to go through your pathway for the evaporated solvent. And then number 4 we call as the thimble. The thimble here is the place where you put your solid sample. Number 5 is the solid sample. Okay, and number 6 is the siphon, where actually when your liquid when you evaporator solvent goes back into liquid, it will go back into your solvent over here. Here is a siphon top, here is siphon exit. In the middle here, we have the expansion adapter. Only the function is only to connect your Socolate chamber with the condenser. The function of, and we have number 9 over here as the expansion adapter, as the condenser, as to condense the evaporator solvent back into liquid. Number 10 and number 11 is the cooling water in. Here is the cooling water out. For the cooling purposes, to turn back our evaporator solvent into liquid. So the process is like this. Okay. You apply heat at the distillation pot, and then your solvent will boil, and some of it will turn into vapor. The vapor will go through this pathway. Okay, I hope you guys don't misunderstood. Between here is actually they have some barrier to prevent the solid goes inside here. It's not some barrier, it's actually ada glass lah kat sini, dia tak pass through. Okay, so your evaporator gas of solvent will the vapor of gas will go through this pathway and go upwards lah, of course, because of the gas they have the less density, so we go upwards. But when during it go through the condenser, we have the cooling process over here. Your evaporator gas of solvent will turn back into liquid and will fall down to the timber, which is containing your sample, and it will pass through your solid and then pass through the siphon. Siphon is like the hollow cylinder of glass connected from the timber to the flux. Dia akan masuk, dia akan sedut masuk dalam, balik ke dalam you punya still pot. It will somehow allow the liquid from the timber to go back into the still pot, so that the continuous process of the extraction can happen. Here is the description. It's not impossible if the question asks you guys, please draw the Socolate extraction and describe, or please describe the Socolate extraction process. It's not impossible. Okay. Solid material containing desired compound will place inside a timber and is loaded in the main chamber of the Socolate extraction. Kita akan letak kat sini lah. The Socolate extractor is placed into a flux containing extractor solvent. Okay, the Socolate is then equipped with a condenser. We call it here as the Socolate extractor or Socolate chamber. We put on the top of the flux containing the solvent, and then at the top of the Socolate chamber, we put the condenser. The solvent is heated to reflux. The solvent is heated, then the vapor travels up the distillation arm. Kalau kata kat sini, dia akan masuk sini lah. Okay. The solvent vapor travels up a distillation arm. Okay. And floods into the chamber housing the timber of solid. Okay, dia akan masuk sini. Di atas ni turn back to liquid, dia akan masuk dalam ni lah. Akan masuk dalam you punya timber yang ada solid sample. The condenser ensures that any solvent vapor cools and drip back down into the chamber housing the solid material. Okay. This the function of condenser. Kalau kata kat sini ada yang dah jadi liquid, dia akan terus drip. But if it's still vapor, when it pass through the condenser, the process of cooling down will happen. It will go back into liquid, drip as liquid, back into the timber that contain your sample. When the Socolate chamber is almost full, the chamber is automatically emptied by siphon side arm, with the solvent running back down to the distillation flux. Okay. When your timber is almost full, dia akan somehow masuk ke dalam siphon and back to the distillation flux, or we call as the distillation pot. This cycle may allow to repeat many times over hours or day. After many cycles, the desired compound is concentrated in distillation flask. Mungkin after one after 1 hour you only get 10% of this sample. Maybe after 1 day you will get about 80%. Maybe after 2 days of this continuous process happen, and you can get extract 100%. After extraction of the solvent is removed, typically by means of rotatory evaporator, yielding the extracted compound, the non-soluble portion of the extracted solid remains in the table and is usually discarded. Alright. Okay. After we extract everything inside the flask, okay, we want to somehow proceed with the rotatory evaporator to somehow to vaporize the solvent to left with our analyte of interest. So analyte of interest can become a very thick liquid or can somehow dry into solid sample, solid analyte of interest. The non-soluble portion kat sini lah, the non-soluble portion of the extracted solid remains the symbol and usually discarded. Kalau kata you punya impurities yang tak soluble, kat sini akan dibuang lah, okay, yang kat sini kita akan keringkan solvent ni sama ada dia become jadi thick liquid at the desired concentration atau we keringkan sampai dia jadi solid. Yang tinggal solid. Here is an example of solid extraction and extract cleanup. We have 10 gram of sludge. Kita guna sludge 10 gram of anhydrous sodium sulfate plus 220 ml of acetone hexane 1:1. We perform the extraction. The solvent of extraction is acetone hexane with the ratio 1:1. We perform the solid extraction for 16 hours. The filter will filtrate using concentrated 1 gram copper powder to remove the sulfur. And we use silica gel cleanup to remove any leftover of the water or H2O. And then the extract can be ready for GC analysis, or if you want to change into solid, or you want to collect a solid sample, solid analyte, so you can proceed to the rotatory evaporator. Do you guys need to remember any of this? I don't think so, but the basic extraction, solid extraction here, you need to somehow understand and remember. The most important key is to understand. If you can understand, you don't need to remember. Alright, here is some of disadvantage of the solid extraction. It's a messy, it's a time consuming, and use lots of organic solvent. Okay, it's a messy because you need, if you can see the fume cover over here, you can see if your thing is not condensed properly, your solvent can vaporize easily to the air. So you need to perform your solid extraction in the fume cupboard. It's not impossible that the vapor of the solvent extraction will go outside. So you may ask, why we can just close the top? Kenapa kita tak tutup je atas ni? Why? Because we close the top over here, we will create the pressure. You know what happen if we create a great pressure, right? We can somehow produce the explosion. Time consuming, it will take days, it will take hours. Use a lot of organic solvent that may hazardous to health. We have the problem with disposal problem, and we need the further concentration step by using, for example, rotatory Solid liquid extraction is useful in many fields, for example in pharmaceutical, environmental and foodstuff. Nowadays, circular apparatus is still common and widely used as reference and standard method in many laboratories for extraction of oil from various materials. I have one experience with circular extraction. I have the pharmaceutical product which is cream pharmaceutical product, so I need to extract the dexamethasone because it's in the form of cream. It's not highly efficient if we just use liquid extraction. So we proceed with the circular extraction. Again, here is mentioned problem with conventional extraction method, use large amount of organic solvent, blah blah blah. Waste disposal problem, extra cost involved, pre-concentration step needed, so it's time consuming, long extraction time. LLE is not really 4 to 8 or 18 hours. It's about 30 to 2 hours only, 30 minutes to 2 hours only at most. But circular extraction, yes, will take a lot of time. Both of the technique of LLE and circular require large amount of sample, and some still carrying contaminants or impurities that can somehow produce interfering background during the analysis. Solution: trend has been towards using smaller quantities of hazardous organic chemicals to minimize environmental impact. Okay, so the solution is we only use the solution is nowadays we try to improve the technique that only use small amount of hazardous organic chemical to minimize the environmental impact and also the health impact to the operator. Okay, the next one we will move into the solid phase extraction. Solid phase extraction is one of the method to somehow overcome the disadvantage of the conventional liquid extraction method, because solid phase extraction is much more selective, and of course the amount of solvent used in the solid phase extraction is very minimal compared to conventional liquid extraction. Okay, we have many other kind of techniques that actually can overcome the problem of the conventional extraction method, such as solid phase micro extraction method. We have the fiber micro extraction method. We also have the what we call as the microchip extraction technique. But for this course, we will only learn on the solid phase extraction method. Okay, the other kind of technique you can explore by yourself. Okay, a solid phase extraction consists of bringing a liquid or gaseous test sample in contact with a solid phase. Let's look on the first part of the sentence. Bringing a liquid or gaseous test sample. So the solid phase extraction method is only suitable for liquid or gaseous test sample. Okay, so your liquid or gaseous sample in contact with a solid phase, as the name mentioned here, is the solid phase extraction, so it use the adsorb extraction technique. So we have the solid particle that can adsorb your liquid or adsorb your gaseous and the light of interest, whereby the light is selectively adsorbed on the surface of the solid phase. So the keywords here is selectively adsorbed on the surface of the solid phase. Okay, let's look into the schemes, the figures or the illustration of the SPE. As we can see here, we have the solid particle inside here. If supposedly this is the ideal condition of the SPE, where we have the pre-filter, we have the particle, we have the disc, and we have the support material. Pre-filter, of course, to pre-filter the sample, and support material is to prevent our particle to somehow keluar lah. Maksudnya kita nak support kita punya particle ni supaya tak terkeluar daripada cartridge. That is why we need this support material. Okay, so back to the sentence over here. The analyte is selectively absorbed. Dia akan absorb dekat solid particle. Dia akan absorb at the particle over here. Okay, so it's selectively. For example, if you want to extract polar compound, so you need to use the polar particle. If you want to extract non-polar compound, so you need to somehow use the non-polar particle of solid phase extraction. If you want to somehow extract, I need ion of the compound of the element. Okay, so you need to use the charged particle. Okay, that is what is meant on the second part of this sentence. Selectively absorb. So let's say you absorb, you have your sample is your analyte of interest is polar, so your particle over here is polar, so it will absorb onto the surface of the particle. So the other compound which is not polar will somehow just eluted thoroughly through the teeth. Okay, cool. So this is how the mechanism of solid phase extraction. Okay, other solvents, liquids or gases added to remove possible adsorbed matrix components. Okay, we will look at after this. Okay, the first step actually we do the conditioning. Maybe we use the solvent just to somehow make the condition of the particle become optimized. So then we loading our sample. Then we will somehow elute our analyte. We will wash the impurities. Okay, because the first step we conditioning the disc over here. We prepare the disc, or we prepare the particle for absorption of the analyte. Then we put our sample. The second step we put our sample. Then our sample is absorbed on the surface of the particle. But we also sure that there is some possibilities of the other impurities also start over here. So the third step is to do the washing process, where we wash the other impurities that is not our desire. Then the next process is elution. Elution is where we put the solvent with the purpose to elute our analyte. Okay. So the mentioned other solvents are added to remove possible adsorbed matrix component. So after we put the sample, our analyte of interest already adsorbed on this phase, we put the solvent for the washing purposes to remove other possible adsorbed matrix component except of our analyte of interest. Then lastly, we put the eluting solvent to dissolve the analyte selectively prior to instrumental analysis. Okay, we already discussed about the figure over here, so we just proceed with the next part. In the SPE principle, we have 4 kind of method. Okay, the first step we call as the conditioning, where we prepare our particle over here to be absorbed by our analyte. Okay, so we active the particle, or we prepare our particle. Okay, then the next one is loading the sample. Then we put our sample. Okay, in the loading our sample, we actually hope that our analyte with the target, our objective is that our analyte of interest will somehow absorb onto the surface. But again, because we only load our sample without any other kind of factor except of the gravitational force, some other kind of impurities will also be stuck or be somehow stuck in the between the particles over here. So we need the washing process. We put any kind of solvent for the washing purposes. Let's say let's say our analyte is polar and our particle here is polar, so it already interact. So we have the non-polar impurities. So the in the washing process, we use the non-polar solvent to somehow remove the non-polar impurities. Okay, and lastly, we somehow do the elution process. Elution process, we again selectively use the correct solvent only to elute our analyte of interest. So the leftover residue of impurities will somehow left in the SPE. Okay, this is how SPE was done. So it is not impossible to be asked in your examination by providing a suitable illustration of SPE. Please describe the method of solid phase extraction method. It's not impossible, Okay. Okay, here is the real figure of the solid phase extraction method. It's actually very small. You can imagine like a syringe, but without the what we call as the penekan dia. We don't have the syringe without the puller. So we put our solvent inside here. Actually, it's very small. So the volume can be from microliter until milliliter or dozen of milliliter. Okay, because it doesn't need a lot of kind of solvent. Okay, we actually have the video over here. Okay, this is how. The first thing first, they do the conditioning by adding the solvent over there. Right. Then they will actually they set up a pump over here. They have a pump over here to suck the solvent over there lah. Actually, this chamber connected to pump, so you adjust the pump at desired flow rate, so it can somehow lagi cepatkan lah dia punya proses. So the next, after the conditioning, we perform the loading step. Loading step is where you put your sample. Again, after you already have put your sample, then you start the pump for the suction process to occur. So they set at 1 drop every 2 seconds. Okay. Oh, sampai situ je. Right, the next process, we do the washing process to remove the impurities, and at the end is elution process. It's not complete this video. Right, the next one we will discuss the advantages and disadvantages of the SPE. Okay, the extract organic phase can be injected directly to the instrument. Okay, so actually if you are doing the SPE, the solvent volume is not that much, it's already selective. You don't need further pre-concentration technique. You don't need another kind of extraction technique after this. So you can actually theoretically, practically just injected directly into the instrument. Many established standard method using this technique. Today's many established standard method using the SPE. Okay. The disadvantage: presence of particulate matter in samples can cause plugging of cartridge. Okay. So because we use the very small particle over here, the problem is if you have the suspended solid in your sample, so somehow your particle over here can somehow clog. Okay, that is the problem. So what you guys need to do to overcome this problem, you need to do pre-filtration process using the filter paper. Large amount of organic waste. If we compare to the conventional, of course it's very good. But if you compare to the next modern techniques such as SPME, solid phase micro extraction technique, or we use the microchip extraction technique, this method actually use quite a number of organic waste. Let's say if we use the chocolate extraction, maybe you need 250 mil. If you use liquid extraction technique, you may use uh, about 250 200 mil of extraction of organic waste. If you are using SPE, maybe you need about 20 mil 10 mil to 50 mil at most of the organic waste. Okay, but it's still okay lah if you compare to the conventional technique. Alright, now we look into the type of SPE phases or packing materials. Selection of sorbent dependent on the analyte and sample matrix. The sorbent have a single retention mechanism. Okay, so this is a type of solvent you don't need to remember. But again, if you heard about C18, mostly is a non-polar solvent. Alright, so here we have the non-polar, we have the polar one, we have the ionic. Okay, as I mentioned here, non-polar solvent, reverse phase solvent for organic compound in aqueous environmental sample, for example surface water. Okay, actually focus on, because why we want to extract the non-polar sample, so we want to remove the polar matrix, which is our water or other impurities, which is polar. If we use the polar as SPE phase, then we want focus for extraction of the polar organic compound in organic solvent lah. Organic, for example, you collect the waste sample from the factory. Okay, you want to analyze. And then the last one, we have the ionic solvent, specific for ionic compound from aqueous or organic samples. Doesn't matter either is polar or non-polar, because we focus on the ionic sample. Ionic sample with the compound with charge, or we focus to analyze to focus on the analysis of the elemental ions. Okay, now we will look into the retention mechanism of the solid phase extraction with the selectively adsorbed phase of the non-polar one. Non-polar lah, I mean. The non-polar is actually, of course, it's a hydrophobic because non-polar is hating water. They will not merge in the water like oil. Hydrophobic. And the thing, the column or anything that related to the non-polar, if the stationary phase or the particle inside there is the non-polar, we also call that as the reverse phase SPE for over here lah. So the typical phase is C18. C8 phenylpolymers. Ni contoh-contoh lah. I don't think you guys need to remember a lot of this, but maybe you guys just need to remember if C18, of course, is a non-polar one, because C18 is a long carbon chain, right? Okay. Most common for aqueous sample. Why is that? Because the polar sample, the aqueous sample, because it will trap the non-polar sample. Huge difference in polarity between phase and water. Organic compound interact with organic solid phase due to their organic frame. If your sample is come from the organic, if your analyte of interest is organic, especially is the non-polar one, or have the non-polar structure, they will be able to absorb onto the surface of the C18, or we call it as the non-polar particle surface. Okay, if we can see over here, we have these two type of compound, how they interact actually. We have the benzene ring here, and we have the alkene functional group over here. So the interaction of the van der Waals will happen from the surface of the particle with the we call as the a part of the compound. Kalau kita tengok sini ada yang polar, ada yang non polar. So kalau kata compound tu is little bit polar, but have the structure of non polar, it also can interact with the surface particle. Alright, this is the mechanism. Maybe the question can ask you what is interaction between of the non-polar SPE. So you need to be able to somehow describe about the van der Waals force. So you can somehow describe that the structure, the non-polar structure from the compound will interact with the non-polar surface of the solid particle of the SPE. Di sini lah. Kalau kata compound, that compound doesn't have any of the non-polar structure over here, they will be just emitted without return in the SPE, solid phase particle. Alright. Okay, the next one, we will look into the retention mechanism for the hydrophilic one, or we call as the polar one, or also we can call as the normal phase. When our particle come with the structure of the polar surfaces, when our particle come from the polar surfaces, so we call it as the normal phase. Opposed to the reverse phase, the interaction between the hydrogen bond, or we can call as the polar interaction or dipole-dipole interaction. Remember, in the non-polar SPE, they use the van der Waals force, but in the normal phase of the SPE, we use hydrogen bonding and dipole-dipole moment. Here we call as the dipole-dipole moment. Here we call as the hydrogen bond lah. Yang ni kita bagi hydrogen bond ni, NH. Okay. So this is how the mechanism of the SPE. Hopefully they don't ask to detail in your examination, but you need to know the basic that the normal phase of SPE is better for interaction with the polar compound, suitable with organic non-aqueous environmental samples. Let's say they ask you, okay, can you describe and give the application of the normal phase SPE? So you guys should be able to answer to that question. Same goes to the reverse phase. You guys should be able to answer that question. The last retention mechanism of the SPE that we will learn today is about the ion exchange. Focus on the ionic interaction. It's suitable for both aqueous environmental sample and also of if you encounter the organic sample, because we only focus on the ionic interaction. Compound that has ionic charge, or you want to analyze ionic element such as sodium ion or chloride ion, also can. You might need to adjust appropriate pH, because some of the compound need to be at the condition of the certain pH before they can have a certain charge. Okay. If the pH is not correct, so somehow your compound will not be able to interact with your adsorber. That's why, especially in ion exchange, for the ionic interaction, you need to do a very careful conditioning, because you remember, right, we have 4 steps of conditioning. We have 4 steps of SPE operation. The first one is conditioning, the second one is loading, the third one is washing, number 4 is eluting, or we call as elution of your analyte. The first one for the ion exchange is very important. You need to adjust, you need to condition your particle adsorbent at the correct charge or with the correct pH, so that when the same analyte of interest come in contact with the adsorbent, they will be able to be absorbed correctly to to the surface of the particle. Same goes when during the elution, you need to somehow have the solvent with the correct pH to be able to elute your analyte of interest from the to dissolve your analyte of interest from the surface particle. Okay. if we look here, we can see that we have the electrostatic and ionic interaction lah. So let's say the question please state the retention mechanism for all types of SPE. So you need to be able to state all three. Okay. And if they ask you, give the hypothetical situation, how you be able to apply the SPE. You need to give an example, or maybe if the question you give two hypothetical situation, so you need to give two hypothetical situation, or you need to give two example of case when you need to use this particular SPE method. For example, for the ion exchange, you say you want to analyze drug. Okay, certain drug is have the certain charge, so you use the ion exchange. Or you want to analyze a heavy metal from the seawater. Okay, so what you guys need to proceed, or you want to analyze the metallic element that is also ionic. Okay, so somehow you correct the pH, you turn the thing into ion, so it will come into contact with the space particle, then they will be able to interact. Okay, right, here is the solvent used in the SPE. Is among the same with the solvent that we have seen during the conventional type of the extraction method in the LLE. The non-polar one is the strong reverse phase and weak normal phase. You kena faham macam ni je lah. Yang lain is about the same. Okay. Kalau if we describe the solvent, let's say they give the table, you need to describe the solvent. Maybe the above one they ask you, okay, if the what is the characteristic of the above one? Give three characteristics. So you can say it's the non-polar one, is strong reverse phase, a weak normal phase, it will not interact with the water. Okay, you can say a lot of things about it. Okay, if we can see here, we have the what we call as the diagram lah, that will be able to somehow give you the idea how to perform the SPE procedure. Okay, let's say if your sample, the first one, if you may somehow think, is your sample aqueous or your sample is organic? Okay, if your sample is aqueous, so your analyte is soluble in water or not? Okay, if your analyte is soluble in water, so you need to focus on the aqueous part. If your analyte is soluble in, for example, hexane, pentane, contohnya, so you need to proceed with the organic part. Okay, if your analyte is charged, so you need to proceed with what we call as the ionic SPE. If your analyte is neutral, okay, you need to use a reverse phase SPE. You need to use a reverse phase, because this is what we bila kita kata neutral doesn't have any charge lah, it's not ionic. If your analyte is charged, either anionic or cationic, okay, you need to, again, for example, you want to analyze chloride. Chloride is an anion, so anion, you need to proceed with the anionic method. Then you again, if your analyte is very weak anion, so you need to use this one. If you have the strong anion, you need to use this one. You don't need to remember a lot of things, but you need to know perhaps the basic. If your analyte is aqueous and also ionic charge, so what kind of SPE catalyst that you need to choose. Okay, here, if your sample is organic, then you know that your analyte doesn't dissolve in water. So after that, you just somehow need to think either it's neutral or charged. If your analyte doesn't have any charge, you try reverse phase, or you try, for me the best one, reverse phase. Okay, If you have charge, then you need to use the ion exchange. Okay, alright. Okay, I mentioned before this, if in aqueous, if you unlike in more soluble in water, I think the best one is not the reverse phase. So you need to use a normal phase lah if you want to track. Okay. If you want to use the reverse phase, maybe you need to use the mid polar. I'm not sure SAZ or SASAX ni mid polar or polar or non polar. If it's totally non polar, it's not really used if your analyte uh, soluble in water. Because why? If your uh, SPE is the reverse phase, which is the solid particle is non-polar, so the interaction of the neutral compound, which is the polar one, we will not interact with the reverse phase, so it will just imitate. So I think the best one here is the normal phase. Okay, that's why I'm feeling very weird why they don't mention about the normal phase. Okay, but if we can see over here, if you dissolve in organic neutral, then you try the reverse phase. This is correct. Then if your analyte also in the organic, for example, because organic we can divide into two, is it either is polar or is non-polar. Okay, such as of the organic the example of organic solvent that is polar is methanol, is ethanol or ethanol. The example of organic solvent that is non-polar, for example, hexane. Okay, the chloromethane. Okay, right. If your analyte is mid to non-polar, so you need to use the reverse phase. I'm not really sure why here you mention the reverse phase, but I think it's more suitable for the normal phase. Again, for here I'm not really sure why it's mentioned for the normal phase, because I think it's if it's non-polar, I think you better use the reverse phase, because from the principles, the non-polar better with the non-polar adsorbent. I will discuss with my colleague about this, but for the time being, we just follow the principle back there lah, that if we use the normal phase, it's better with the polar, have better interaction with the polar analyte. Kita tengok sini lah, we have the polar punya phase particle, we want to somehow extract our polar analyte. Okay, but yes, I will if there is anything, I will post it inside the e-learning about this, because it's like not really correct. If it's a mid polar, then it should be okay for the normal phase or the reverse phase, but if the non-polar, I think it's better if we just use the reverse phase SPE. Okay, 3 goals of SPE is for purification or cleanup. Here is the example of before SPE, we have a lot of background interference come from the impurity. By doing the SPE, we can somehow remove a lot of interference, so we can get a cleaner reading, so we can get a better qualitative and also quantitative analysis. The second one, we want to concentrate our analyte. For example, our sample is 1 liter. Okay, let's say your sample is a very trace, and the amount of your sample is 1 liter, so you can pre-concentrate by 1 mil. You loading your sample 1 liter inside the SPE tube, but at the end you eluted with 1 mil of solvent. Maksudnya daripada 1 liter tu, you at the end the final elution is 1 mil. It depends on the final concentration you want. For the elution process, you can adjust by with your intention lah, mana yang you nak sebenarnya. solvent switch from water to methanol. So let's say you want to analyze using GC, you want to analyze using GC, but you know that water is not good for gas chromatography. So how you be able to remove the water content from your sample? So what you can you do is that you perform the SPE. Then at the end you will elute your sample using methanol. So that is other way how to remove the water from our sample nitrate, so we will be able to perform gas chromatography. Okay, but when I mention about it, it doesn't mean that GC is not okay for water. It depends on the column. If the column is non-polar, then it should be okay. But if your column is mid-polar to polar column in the GC gas chromatography, the usage of water is highly not recommended. Okay, again, if the column is the non-polar one, the application of the water is not that a problem, because the problem we have in the water is just on the back pressure. But if we use the polar column in the gas chromatography, the problem is the water can somehow damage your column. Okay, that is why we need this solvent switch lah. Okay. Okay, SPE application per sample preparation. Here is the original sample. Okay, here is example to concentrate on the light. Okay, so here is original sample. Okay. After you do the analyte concentration, then after the SPE process, you will be able to have a better detection. Okay, this one. Okay, ini is the okay, yang ni ke sini. Okay, yang ni dia dua benda berbeza Okay, this the concentration. Yang ni you somehow to remove the impurities. First sample extraction, you have a lot of impurities, so you can see the background signal is a lot, so you won't get a very good baseline. But using the SPE, you will somehow have a better removal of the impurities, so at the end you can get rid of the background interference a lot better. Okay, here is the automated solid phase extraction system. I don't have any experience on this. I'm not really sure if we have this on in UTM, but the one in the video in the earlier slide, we have that, and I have that chamber. Okay, I think that's it for the sample preparation for organic phase. You may somehow comment in the section, comment in the YouTube for your attendance. Same goes to the what we call as the, if you have any question, you can post it there as well. So I think we finished about the sample preparation for organic and lights. That's it. Thank you.